In this presentation, I would like to provide a brief introduction to circuit simulation and device modeling. For a more comprehensive exploration of this topic, I encourage you to refer to a more detailed course given by the link here. Circuit simulation and device modeling are closely interconnected, as a practical device model ultimately needs to be implemented as computer code that can be executed within a circuit simulator like SPICE. Therefore, rather than starting with device physics, as is common in many device modeling courses, I will introduce the concept of device modeling from the perspective of circuit simulation. So, let's begin by defining what a circuit is. A circuit is formed when various components, referred to as devices, are connected together. Here's an example of a circuit where each device is represented by a model implemented through computer code. When two or more devices are connected, they create what we call nodes. In the diagram, you can see three nodes labeled N1, N2, and N3. Additionally, there are four branches labeled B1, B2, B3, and B4, which correspond to the four devices in the circuit. Each device model calculates the current it will draw from the terminals to which it is connected based on the terminal voltages provided. For instance, if the device is a 100 ohm resistor, the magnitude of the current drawn from the positive terminal is positive V over 100, while the current drawn from the negative terminal is minus V over 100. In circuit simulation, our goal is to determine the node voltages in response to one or more signal sources. For a meaningful circuit, at least one device in the circuit must function as a power source. Otherwise, the simulation would yield a trivial solution where all node voltages are zero. So, how does the simulator tackle this problem? Initially, it makes an arbitrary guess for the values of all node voltages. But how can we verify if these guesses are correct? The answer lies in Kirchhoff's current law, or KCL, which states that for a circuit to operate correctly, the sum of all currents flowing into or out of a node must equal zero. If this condition is met for all nodes, we can conclude that we have found the correct solution. However, since the simulator starts with arbitrary guesses, it is unlikely that KCL will be satisfied initially. If the KCL condition is not fulfilled, the simulator will generate a new guess and repeat the process until the condition is satisfied. Throughout this iterative guessing process, we aim for each subsequent guess to be an improvement over the previous ones in finding the solution. This is typically achieved using an iterative method. To clarify how the simulator operates, we need to express the problem in more formal mathematical terms. However, there's no need to worry. I will keep the mathematics to a minimum to effectively define the problem without delving into the details of the calculations. First, let's assume the circuit has n nodes. We can gather all the node voltages, V1 to Vn, to create a voltage vector V, which represents all the node voltages in the circuit. Next, we can calculate the sum of the currents entering each node. For instance, the sum of currents entering node 1 is a function that depends on all the given node voltages, or the voltage vector V. At this point, the specific form of the function is not important, so we will simply refer to it as I1. We repeat this process for all nodes, resulting in a collection of total currents entering each node, labeled I1 to In, all of which depend on the voltage vector V. We can then compile these current components into a current vector I. In this context, we have a current vector I as the dependent variable, which is influenced by the node voltage vector V. With these definitions in place, we can express the problem in circuit simulation as a straightforward mathematical statement. The objective of circuit simulation is to find the values of the voltage vector V, such that the current vector that represents the sum of currents entering each node in the circuit equals zero. In equation form, this means solving for V such that I of V results in a zero vector. To find a general solution to the system of equations, an iterative approach will be used to arrive at a numerical solution. Typically, we employ the Newton-Raphson method to determine the numerical values of the voltage vector V. Let's take a moment to understand the Newton-Raphson method. It's easier to illustrate this process in one dimension before extending the concept to multiple dimensions. For a single variable function representing current in terms of voltage, we can perform a Taylor expansion around a point V0. This results in the following expression. We only retain the constant and linear terms while ignoring the higher order terms. Physically, This means we are using a linear function to approximate the original function at the point v0. This approximation predicts that the solution for the current I equals 0 occurs at v1. While this prediction may not be exact, it brings us closer to the actual solution. We can then use v1 as our new guess and expand the function around this point. This process yields a better approximation of the solution. We continue this iterative process, with each new guess getting progressively closer to the true solution. To find the next guess, v1, we set our approximated equation to 0 based on our current guess v0, and solve for the required voltage V. In this example, v1 is determined by the equation provided. More generally, the formula for finding the next solution at the k+1 iteration involves both the numerical value of the function we want to solve and its derivatives at the current kth iterative point. The derivative essentially guides us on the direction and step size for our next guess. It's important to note that the derivative only influences how quickly we converge to a solution and not the accuracy of that solution. If you're lucky, using an incorrect derivative can sometimes lead to better convergence by chance. However, this kind of luck is uncommon. In vector form, the iterative equation looks similar, but we replace scalar variables with vectors. The same concepts still apply, and the multidimensional derivative helps us figure out which direction to look for the next solution. By rearranging the equation to eliminate the fraction, we can write it in a simpler form. When we take the derivative of a vector function with respect to a vector variable, we end up with a matrix. If we break down the equation into its individual components, it looks like this. This matrix shows how current changes with respect to voltage and has units of conductance. It forms a transconductance matrix that includes the partial derivatives of all node currents with respect to the different node voltages. We typically refer to this as the Jacobian matrix of transconductances. The iteration process converges when the voltage vector we calculate makes the current vector equal to 0, or when the value of next iterative voltage vector is the same as the current one. It is important to note that if the system consists only of linear elements, it will converge after just one calculation and no iterations are needed. Referring back to our example circuit, the expanded matrix equation appears as shown here. The total current at each node is the sum of the branch currents connected to that node, meaning each branch contributes a current component. Essentially, a circuit simulator like SPICE functions as a linear matrix equation solver. In this context, what happens when a device is added to an existing circuit? The new device adds a circuit component to each node it connects to. For example, if we add a MOSFET with its drain, source, gate, and body connected to nodes 1, 2, 3, and 4 respectively, it will add ID to node 1, IS to node 2, IG to node 3, and IB to node 4. In terms of the matrix equation, adding a device will simply add the corresponding currents and conductance to what is already present. This is why, in the simulator input deck, we list each device individually. When the circuit simulator encounters a device, it constructs the circuit matrix by adding each device one at a time. Now that we have a basic understanding of the circuit simulation process, we can switch our attention to device models. What are the requirements for a device model? It depends on the type of simulation being performed. What we described earlier is DC simulation, where the simulator generates the output signal based on another signal, typically voltage or current, under steady-state conditions. For this type of simulation, the device model must accurately produce the terminal currents when the terminal voltages are applied. The model also needs to produce well-behaved current derivatives, primarily for convergence purposes. While the accuracy of these derivatives does not impact the overall accuracy of the simulation, it is crucial for ensuring convergence during the iterative process. Let's use an example to illustrate why the behavior of the derivatives is more important than their accuracy. It is common to use piecewise fitting for experimental data, as shown in this figure. Below a critical VD set point, we fit the data using the given equation here. Once the voltage exceeds the VD set point, we assume the current remains constant. This creates a discontinuity in the derivative at the VD set point. In general, the simulation works well in most regions, except near the VD set point. For instance, if we start with a guessed VD input slightly below VD set, the simulator will project the next result based on the derivative, resulting in a value higher than the actual current. Using this new data point for iteration will lead to another point that is also incorrect. In such cases, the solution may oscillate, making convergence difficult. If we smooth out the breakpoint to ensure continuous derivatives, we can avoid oscillations. Therefore, the smoothness of the derivatives is sometimes more important than their accuracy. Another type of simulation performed by a circuit simulator is transient or time domain simulation. In this situation, the input signal varies with time, and the output signal is calculated based on this time variation. Unlike DC simulation, capacitive currents caused by the movement of charges must be included. To calculate the charging current, a different set of equations governing the change of terminal charges as a function of terminal voltages must be derived, along with their derivatives, known as transcapacitances. These equations are highly nonlinear, making transient simulation more challenging to solve than DC simulation. Similar to the current voltage equation, the model must have an accurate charge versus voltage relationship to achieve accurate simulation results. Additionally, the transcapacitances are essential for ensuring convergence. At this point, I would like to add an important remark. For a correct physical model, the current versus voltage and charge versus voltage relationships should be consistent, as they both arise from the same charge motion. However, this requirement makes data fitting very challenging, because the same charge must satisfy two different sets of criteria, and data. As a result, additional empirical parameters are often added to the IV and QV model separately to fit the different set of data. Consequently, consistency between the IV model and the QV model is not guaranteed in most cases. If inductance must be included, another set of flux versus voltage equations needs to be derived. Fortunately, most physical inductances are generally linear, which minimizes convergence issues. In addition to DC and transient simulations, a circuit simulator can also perform AC or frequency domain simulation. In AC simulation, an operating point is required for a given input signal, which is determined through DC simulation. Once the DC solution for that specific biasing point is found, the current and charge versus voltage characteristics around that point are linearized and replaced with a linear function. This approach is generally valid when the simulation is focused around the biasing point, which we refer to as small signal analysis. In this case, the slope or gain of the circuit around the biasing point is determined by how conductance and capacitance change with frequency. Therefore, unlike DC and transient simulations, the accuracy of AC simulation relies heavily on the accuracy of the derivatives. The current voltage characteristics are primarily important for identifying the biasing point. Once the biasing point is established, convergence issues are typically not a concern, as the circuits have been linearized. From this, we understand that DC, transient, and AC simulations are essentially different programs operating with different models. As a result, there is no guarantee that they will produce consistent results, even though we expect the results obtained from different modes of simulation methods are close enough. Now that we have covered the basics of circuit simulation, let's move on to device modeling. To keep things straightforward, we will just cover DC simulation, which deals solely with the relationship between current and voltage. Once you grasp how to create the current model, you can apply the same principles to develop the charge model. Since the main function of a model is to produce terminal currents and their derivatives, any black box that can produce the required outputs can be considered as a current model. If we do not have any data and just want to predict the behavior of a circuit's numerical solution from TCAD tools can be used. These TCAD models predict the current-voltage relation by directly solving the Poisson's equation, drift diffusion equation, and continuity equations, which are differential equations governing the electrostatic and carrier transports in the device. However, this kind of model takes a long time to generate a data point, and not very practical even for some medium-scale circuits. In another extreme, we may have a device governed by unknown physics, but we do have measurement data. In this case, we can construct a table to map the terminal currents at the given terminal voltages, forming a table lookup model. When the simulator provides a guess for the terminal voltages, the device model simply looks up the table to provide the corresponding currents and derivatives. For any missing data points, the model can generate them by interpolating between neighboring data points. Compared to T-card-based models, table lookup models are fast during simulation. However, they lack a physical description of the device operation. More importantly, they have no predictability beyond the provided data. This means that the current voltage relationship for all devices used in the circuit must be included in the table for accurate simulation. In addition, extracting the necessary physical data requires significant effort. Despite this, table lookup models have been widely used in the simulation of many emerging devices before the detailed physics of their operation is fully understood. Now we understand that TCAD models are physically accurate but can be slow for simulation. In contrast, table lookup models lack physical insight, yet they are fast and can accurately reproduce measurement data. Between these two extremes, we find compact models, which are the most commonly used models for circuit simulation. In compact models, the relationship between terminals currents and voltages is described by analytical equations, typically expressing terminal currents as an explicit function of terminal voltages. Depending on the complexity of these equations and the number of parameters involved, compact models cover a wide range of approaches that represent the trade-off between physical accuracy and simulation speed, sitting between TCAD models and table lookup models. This is also the type of models that most researchers are focusing on. From now on, we will focus on the development of compact models. In general, there are two different approaches to developing compact models: the empirical approach and the physical approach. In the empirical approach, the goal is to fit all measurement data accurately using the most suitable mathematical function. While this type of mathematical model can fit experimental data quite well, it does not offer much insight into the operation of the devices. It's worth noting that a table lookup model is an extreme case of an empirical model. Another approach to developing compact models is based on device physics, where the model equations are constructed using physical principles rather than solely relying on data. For example, we can calculate the channel charge based on factors such as gate oxide thickness, gate work function, and channel doping. If the underlying physics are accurate, we expect the model to align well with the physical data. However, matching measurement data is not easy, as our understanding of device operation may not be perfect, and physical devices often exhibit many non-idealities. Generally speaking, physical models are less accurate when applied to a specific device's data. However, they offer greater insight into the physical operation of the device and allow for predictions of device performance beyond the given data. Researchers typically prefer physical models over empirical models, especially in research publications. In practice, a compact model usually serves two different purposes. First, it is expected to be physically accurate in order to provide insight and understanding of device operation. This understanding allows researchers to exchange ideas, refine device structures, and make predictions that contribute to optimization and decision-making processes. Secondly, it should also be mathematically flexible to fit all measurement data. It is difficult to achieve both. It is because the development of physical models is typically based on an ideal structure. In contrast, real devices often possess many unique features that differentiate them from this ideal structure being modeled. As a result, no matter how diligently a model developer works, the physics of the model devices is different from that of the actual devices, leading to inaccuracies. Let's use an example to illustrate this. For a real MOSFET, we can typically assume that the width is confined to a specific dimension, with no physical structure beyond that. Based on this assumption, we can predict the current voltage characteristics as shown here. However, depending on the isolation technology used, fringing electric fields from the sides can lead to different types of early turn-on, primarily affecting the subthreshold region. This phenomenon is challenging to describe in a physical model, unless we can specify the structure accurately, like in TCAD models. The real situation is even more complicated, because different foundries may employ different device structures. Yet the model is expected to be universal enough to fit data from different foundries. To address this issue, we often add extra parameters and modify the equations, allowing us to adjust certain parts of the curve to fit the data. For example, a parameter like V-off can be used to tune the subthreshold region of the curve while leaving the turn-on region unchanged. This approach generally makes a physical model more empirical. As a result, a practical compact model is usually a blend of both physical and empirical models, combining their physical and mathematical characteristics. Current industry practices also lead compact models to be more empirical. While academic models developed by researchers primarily aim to provide insights into device operation, they often require significantly more time to fully understand the underlying physics in order to accurately incorporate them into the model. However, the industry cannot afford to wait. It needs to begin designing circuits even before a technology is finalized to ensure a quick time to market. In this scenario, a device model is essential for design, even before the device structure exists. Therefore, industrial models must have a physical core that offers an initial estimate prior to device creation, while also being flexible with numerous adjustable parameters. This flexibility allows for the incorporation of unknown effects into the model once they are observed without full understanding. Additionally, the model must be efficiently integrated into a circuit simulator. In 1996, the BSIM 3v3 model was chosen as the first industrial standard model by the Compact Model Council for use in the semiconductor industry. The primary reason for this selection was not the superior physical accuracy of the model, but rather its flexibility to accommodate various datasets and its efficiency in circuit simulation. This highlights the differing requirements between academic models and industrial models. After understanding the requirements of a compact model and its application in circuit simulators, it's helpful to explore the process of constructing an industrial standard model. We will use some equations from the BSIM-3 model as an example, as it was the first industrial standard model adopted by the industry. By walking through the model development process, I hope this presentation will provide you with a foundational understanding of the basic concepts of device modeling. To begin with, let us recall that the role of a model in circuit simulation is to produce the currents and conductances of a device when the terminal voltages are given. To construct a MOSFET model, we can use the classical equations of a MOSFET as the starting point. When the MOSFET is turned on, the current of a MOSFET in the linear region is given by the equation here. This equation only applies when the MOSFET is turned on and the gate voltage is larger than Vt. The behavior of this equation at a particular Vg is shown in this figure on the right. When the drain voltage becomes larger than Vg minus Vt, the equation predicts the current to decrease, which is non-physical. So the saturation region equation given below is introduced to keep the current to be constant for Vd larger than Vg minus Vt. This is called the saturation region current equation, and the voltage Vg minus Vt is called the saturation drain voltage. When Vg is below Vt, we assumed the MOSFET is perfectly turned off and set the current to be zero. Using these three equations, we can plot the current as a function of Vg at a specific drain voltage Vd and the current as a function of Vd at a specific Vg. According to the equations, there are two critical points where the equations switch from one behavior to another. One occurs at Vg equal to Vt, and the other at Vd equal to Vg minus Vt. It is important to check the currents and conductances at both of these breakpoints to ensure they are continuous. Fortunately, in this case, they are continuous. Therefore, these classical MOSFET equations provide a reasonable model for circuit simulation. However, we know that the classical MOSFET equations are not accurate enough. In particular, the current of a real MOSFET below the threshold voltage is non-zero. To address this, we can modify the drain current equation for Vg less than Vt by incorporating an exponential function with Vg, which is derived from physical principles. At the same time, we keep the same equations when the MOSFET is turned on. With this new equation, we can take a look at the predicted behavior of the MOSFET with respect to Vg. For the region with Vg below Vt, the current is no longer zero, and it is given by the red line shown in the figure. It is a bit exaggerated to create a visual effect to illustrate the idea. There will be a discontinuity in the current at Vg equal to Vt. The discontinuity will become more obvious when plotting the current in log scale, which is given in the graph below. This kind of behavior is not acceptable, and we have to find a way to remove the discontinuity. We know that actual current will change from the exponential characteristics to the polynomial characteristics as shown with the blue line in the graph. The question is how to transit from one equation to another. In general, there are two different methods to handle it. The first method is to derive more accurate equations based on the device physics. For example, using the surface potential approach, we can derive the current equations as given below, which is much more complicated than the simple model. This equation provides a natural fitting from the subthreshold to the turn-on characteristics of a MOSFET. However, this approach has some drawbacks. First of all, the equations used to calculate the surface potential, phi s, at the source and drain are transcendental equations without explicit form. So iteration is needed to solve for the surface potential, and it is not very simulation-friendly. Fortunately, the number of iterations can be reduced by providing an appropriate initial guess. Secondly, the complex form of the equation makes it difficult to adjust part of the curve without affecting the other parts. For example, assume the turn-on region is accurately fitted already, and only the subthreshold region needs to be adjusted. It is difficult just to change some parameters to adjust the subthreshold region without affecting the turn-on region. The second approach is to connect the two equations for the two different regions using a smoothing function in the transition region. The transition needs to ensure the current and the conductions are smooth and continuous. This is not a simple task, as it requires many parameters to adjust the transistor function to meet the criteria at the boundary points. Also, the transistor must accurately reflect the correct characteristics for all drain voltages, not just one. The BSIM models have tried to implement different smoothing functions, but none were satisfactory until the release of the third version of the BSIM family. In BSIM 3, a naturally smooth function that transits from exponential to polynomial dependence on the running variable is used to achieve the smooth transition. It defines a variable called VGST effective, given by the expression here, where VTH is the thermal voltage, KT over Q, and N is the ideality factor. After VGST effective is defined, it will be used to replace all the Vg minus Vt in the on-region equations. The subthreshold region equation is no longer necessary as VGST effective is always positive. As a result, the on-region equations can be extended to the region with Vg less than Vt. Let's examine how the smoothing function operates. When the difference between Vg and Vt becomes very large, specifically much larger than 2NV thermal, the exponential term also increases significantly. In this case, we can ignore the 1 in the parentheses. Once we remove the 1, the natural logarithm and the exponential functions cancel each other out. It also leads to the cancellation of the 2NV thermal terms. In such a case, VGST effective just becomes Vg minus Vt. The on-region current equations just give the value of the classical MOSFET model, as shown with the blue line in the given figure. When Vg becomes smaller than Vt, Vg minus Vt becomes negative, and it is on the other side of the line, Vg equal to Vt. When the magnitude of Vg minus Vt becomes much larger than 2NV thermal, the index of the exponential term becomes a very large negative number, and the exponential term becomes a very small positive number. We can express the quantity inside the logarithmic term to be 1 plus x, where x is a very small number given by the exponential term. If we expand the natural log of 1 plus x, the following series will be obtained. Assuming x is very small, we can ignore all the second-order term onward, and we will have the natural log of 1 plus x approximately just equal to x. Putting it back into the original equation, we will have VGST effective equal to the expression given here, with an exponential dependent on Vg. In the subthreshold region, VGST effective will be very small, and it is most probably to have Vd larger than VGST effective. So we can safely apply the saturation equation and extend it to the subthreshold region by substituting the value of VGST effective to the Vg minus Vt term. The following equation is obtained. As shown by the equation, the drain current will have an exponential dependent on the gate voltage. It will give an exponential trend in the graph as shown here. The trend is now correct, with the current follows an exponential function at Vg below Vt, and finally becomes linear at high Vg. However, the magnitude of the current in the subthreshold region may not be correct. It is because there is no parameter to tune the current in the subthreshold region, and the property of the equation is fixed by values from the on-region equation. Some might propose to change the expression of VGST effective. However, this is also difficult because any small changes to the expression can cause incomplete cancellation of the constants. That will affect the convergence of VGST effective to Vg minus Vt for large Vg. This in turn affects the accuracy of the on-region model. To achieve better fitting, the VGST effective function used in BSIM3 is given here. The purpose of this complicated function is just to introduce a fitting parameter Voff to provide an offset to the voltage axis in the subthreshold current. The quantity in front of the exponential term in the denominator is to provide some physical meaning of the expression. But it is not important as it can be absorbed into Voff, which is an arbitrary fitting parameter anyway. Now, let's look at the behavior of the new VGST effective. In the on region, Vg is much larger than Vt. Assuming Voff is relatively small, this means Vg is also much larger than Vt plus 2 times Voff. As a result, the index of the exponential term becomes a large negative number, making the exponential terms very small compared to 1. Therefore, we can ignore them in the denominator. This means that VGST effective simply takes the value of the numerator, which remains the same as before. That means the current equation will converge to the conventional equations in the region with Vg larger than Vt, as shown in the graph. As the denominator is always larger than 1, you may expect the current calculated with the new VGST effective will always be slightly less than that calculated with the original VGST effective function. When Vg minus Vt minus 2 times Voff becomes very negative compared with minus 2 then V thermal, the exponential term in the denominator will become very large, and the one in the denominator can be removed. The natural log and exponential function in the numerator can be approximated by an exponential function like what is discussed before. Then, the exponential function in the numerator and denominator can be combined to give the following expression. It shows that the Voff term provides an offset to the variable Vg in the subthreshold region of the equation, but it does not affect the on region. By changing the value of Voff, we can shift the subthreshold region curve in either direction to better match the physical data. Another advantage of this approach is that the function becomes infinitely differentiable, so we do not have to worry about the continuity of the function or its derivatives anymore. After introducing the VGST effective function, the equation describing the MOSFET simplifies from 3 equations to 2. However, whenever there is a switching between these 2 functions, there can be potential concerns at the boundary point. In particular, due to velocity saturation, the transition from the linear region to the saturation region happens at the saturation drain voltage VDSat, which is smaller than VGST effective. The new characteristics is shown in the figure here. While the current remains continuous after adjusting the saturation drain current, but the derivatives at the VD set point become discontinuous. To ensure that both the current and the derivatives are continuous and smooth, another smoothing function is used. This is accomplished by introducing a new variable, VDS effective, defined by the expression provided here. We then use VDS effective to replace the VD term in the linear region MOSFET equation. As a result, we no longer need a separate equation for the saturation region, allowing us to use a single equation to calculate the MOSFET current across all operating regions. The characteristics of VDS effective are shown in the figure. From the figure, you can see that for small VDS values below VD set, VDS effective is approximately equal to VDS. However, when VDS exceeds VD set, VDS effective gets clamped at VD set. The value of delta controls how abruptly the switching occurs. You can easily verify the properties of this function using software like Excel or MATLAB, though I will not cover that here. With the introduction of both VGST effective and VDS effective, we can describe the drain current of a MOSFET with a single equation, ensuring the continuity and smoothness of the function and all its derivatives. After discussing how to develop a simulator-friendly model, the next subject to be discussed is the way to improve the model's accuracy across a wide range of geometries and biases. To illustrate this, we will use the process of developing the threshold voltage model as an example, showing how to align it with a broad spectrum of existing data. To start the process, we measure the drain current of a typical MOSFET as a function of gate voltage at a very small drain voltage, around 50 mV. Next, we identify the maximum slope of the graph, which corresponds to the maximum transistor conductance, Gm. We extend this slope until it intersects the VG axis, giving us the measured threshold voltage, which we call VT0. This is the initial threshold voltage we obtained. VT0 corresponds to the threshold voltage found in many textbooks, which is expressed here. However, since we do not know the doping concentration and other related parameters, we obtain it through direct measurement instead. Using VT0 as the threshold voltage suggests that it is a constant independent of geometry and bias. However, just a constant is not accurate enough, and we need to enhance its precision. The first factor we need to enhance in the threshold voltage model is its dependence on body bias. When a different body bias is applied, the drain current shifts accordingly, leading to different values of VT. To account for this, we add a correction term, delta VT1, to the VT expression. Delta VT1 is defined by a common expression where gamma is the body factor and phi b is the difference between the Fermi level and the intrinsic Fermi level of the silicon substrate. In this process, we introduce some new parameters to accurately determine VT, which are listed here. In the BSIM3 model, the body factor gamma is referred to as K1. The value of phi b is calculated using other parameters, including substrate doping and channel doping. However, to keep things simple, we will treat phi b as an independent parameter in this discussion. The VT expression we have till this point can only handle cases with uniform body doping. In real devices, substrate doping can be non-uniform, as shown in the figure. When different body biases are applied, the edge of the depletion region moves through areas with varying doping concentrations. When we measure VT as a function of the square root of 2 phi b minus VBS, we observe different slopes due to these varying doping concentrations, resulting in different values of gamma. To account for this effect, we add another correction term, delta VT2. Delta VT2 is defined by the expression here, where K2 is a fitting parameter that adjusts the value of K1 in certain parts of the curve. To include this effect to the model, we introduce one additional parameter related to VT. Up to this point, the VT expression does not have a channel length dependence. When we plot the threshold voltage against channel length, we see the characteristics shown in the figure here. As the channel length decreases, VT first increases and then decreases. The extent of this increase and decrease depends on the gate oxide thickness. The region where VT increases with a reduction in channel length is known as the reverse short channel effect. The generally accepted explanation for this behavior is illustrated in the figure here. The distribution of channel dopants is not uniform along the channel length, with higher concentrations near the source and drain. This non-uniformity may be due to the halo structure or other processing-related effects. The dopant distribution is assumed to follow the pattern shown in the graph here. When calculating VT, we should use the average dopant concentration rather than a uniform substrate dopant concentration, Na, in the middle of the channel. To find the average dopant concentration, we define the effective dopant concentration, N effective, which is given by the equation here. This is simply the weighted sum of the dopant concentrations along the channel. After some mathematical manipulation, all the newly introduced parameters can be combined into a single term NLX, which is defined by the expression here. Since we do not know the values of Lx and MP, NLX just serves as another arbitrary fitting parameter, even though it has some physical meaning. Once we define NLX, we can introduce another VT increment as delta VT3 with the expression provided here. As a result, the parameters associated with VT increase by 1, as listed here. After addressing the VT increase due to reverse short channel effects, we now need to consider the VT drop at even smaller channel lengths. To do this, we introduce another incremental term, delta VT4, defined by the expression provided here. I will not go into the derivation of delta VT4, as it is not the main focus of this presentation. If you are interested, you can refer to the following paper yourself. In this expression, 3 new parameters dVT0, dVT1, and LT are introduced. The parameter LT can be further expressed using another new parameter dVT2, as shown in the following expression. After adding the new increment delta VT4 to the VT expression, the total number of parameters associated with VT is increased by 3. At small channel lengths, VT decreases with increasing drain voltage due to drain-induced barrier lowering, or DIBL, as illustrated in the figure. To account for this drain voltage dependence, we introduce delta VT5, which captures the change in VT with respect to the drain voltage. This adds yet another increment to the VT expression, along with 3 additional parameters. The process continues by adding delta VT6 to account for the width dependence of VT, which introduces 3 more parameters. The assumption for adding VT dependence on W and L is that the changes in VT with respect to W and L are uncorrelated. However, this assumption is not accurate, as the way VT varies with L can differ between wide channel and narrow channel devices. To address this correlation, we introduce delta VT7, which is a function of the product of W and L, as defined by the expression here. This delta VT7 is then added to the VT expression, increasing the number of parameters by another 3. The process can continue by incorporating the effects of other parameters on VT, such as temperature. By adding more parameters, we enhance the fitting capability and accuracy of the model. In this process, we usually add 3 parameters to account for the dependence on a new variable. This is because most physical quantities have a monotonic relationship with other parameters. In these situations, we typically choose an appropriate function, often polynomial or exponential, to match the trend of the data, which is usually either concave up or concave down. One parameter sets the initial point, another establishes the final point, and the third controls the rate of change. This is a brief overview of how to construct a simulator-friendly compact model and improve its accuracy. While it doesn't delve into the detailed physics, it covers the general process of model construction. Through these examples, I hope you have gained some insight into how compact models are developed and refined. I want to emphasize that having the correct physics alone is not enough for a model to be useful. It must undergo several processes, including mathematical refinement, convergence improvement, parameter extraction methodology, and experimental verification before it can really be used in circuit simulators. Many models never reached completion and disappeared after publication. As I prepared this tutorial, AI has begun to make its way into the world of compact modeling. Instead of developing a compact model from scratch, the process can be accelerated by using physical data to train models constructed with neural networks. These models function more like lookup tables, but are much more powerful. However, we still want to incorporate some known physics to ensure their functional correctness. This approach is still under active research, but it goes beyond the scope of this tutorial.